Hello, welcome to Vastiversity. And today we're going to be continuing with rectangular coordinates, graphs, and linear equations. Okay, so let's start with the rectangular coordinates. So rectangular coordinates are also called Cartesian coordinates. Okay, and some of the properties of the Cartesian coordinates is that they are the most popular coordinates to use in mathematics. And the rectangular and the Cartesian plane was invented by René Descartes. So, and that was roughly in 17th century. So to be exact, 1596 to 1650. That's when he lived. A very great mathematician. He's a French mathematician. He essentially invented this system. So, two real numbers intersecting at the right angles form a Cartesian plane, right? So what is a right angle? A right angle is a 90 degree. So let's actually draw one. And I actually do have it predetermined. Or actually, yes, let's use a full scale, right? So here it is. I have two lines which are perpendicular to each other, right? And we're gonna label this as x-axis and this as y-axis. And of course, based on the scale, we can treat it as a number line. So 1, 2, 3. So 1, 2, 3. This is positive. Then 1, 2, 3. This is positive. Right at the very center, we got 0. Okay, and then to the left, we have -1, -2, -3. And on the bottom, we have also -1, -2, -3. Okay, so essentially, what we can tell, we can say, well, this part of the rectangle, right, we call it quadrant 1. Quadrant 1, or just Q1, right? Q1, and that gives us, quadrant 1 gives us that x is positive and y is positive. Right, quadrant 2, which we're going to call Q2, x is negative, so x is less than 0, and y is less than 0. X is greater than 0, y is greater than 0, and y is actually greater than 0 here. So for the third quadrant, which is right here, so as you can see, it goes counterclockwise. X is negative, y is negative. And for the third quadrant, for the fourth quadrant, we have y to be negative, x to be positive. So x is positive, y is negative. Okay, and of course, we can have points, right? We can have points based on the values of x and y. So for example, to have a better understanding of what's happening here, let's go ahead and take a look at this image right here. Here is the y-axis and the x-axis, and we have an order pair. So an order pair, it's always written as x comma y, right, where the first coordinate is the x coordinate on the x-axis and the second coordinate is the y coordinate on the y-axis. So in our case, for example, I want to label it as, let's say I want to say a point 1 comma 2, right? So 1 is right here, 2 is right over here, so my point is going to be right here. This is my point of 1 comma 2. Okay. And then, for example, 0, 0. 0, 0, that's the intersection point. It's going to be over here. Perfect. So we can have a lot of things on the Cartesian line. As one of the examples, what is the great use of it is we can find a distance. right? We can find a distance. Let's say that we have 2 points, right? 2 points. Point number 1 is going to be x1, y1. Point number 2 is x2, y2, right? So essentially, what we want to find what's the distance, right? We want to find this line right here. From here to here, we want to find the value of it. Okay, so how would we do that? The way we're going to do it is by using the distance formula. And the distance formula is related to Pythagorean theorem, right? And in case you forgot what a Pythagorean theorem is, I'm going to remind you. I'm going to remind you right here. A quick reminder. So Pythagorean theorem is if we have a right triangle, right? A right triangle. And in our case, we do have a right triangle. Our entire coordinate system is a right triangle here. So the Pythagorean theorem says a squared plus b squared. So the two sides of the triangle squared and added together is equal to the hypotenuse squared. So the longest side is the hypotenuse. So in our case, we have this is our side A, this is our side B, right? And we're given this is A, which is equal to absolute value of y squared minus y2 or minus y1, and B is absolute value of x squared minus x1. Okay, so then what would be the distance formula? The distance formula would be as following. So in the flat plane, in the 2 coordinate system, we will have that the distance between the point x1 and x2 is as following. And the way we label the coordinate system, so you know when we had a real number, right? So real numbers are labeled like this, right? This is real numbers. But now we are scaling it to 2 essentially real number lines, x and y. So we would say r squared, right? It's going to be Cartesian coordinates, or essentially the second dimension, right? We have 2 dimensions here. So second dimension, right? We're going up and right or left, right? Okay. So we have the following. Now, since we know the distance formula, let's take a look at an example. Let's take a look at an example. So example is going to be the following. So let's say we have a point -2, 1 and 3, 4. Then we're going to have a distance, right? We want to find the distance between them. So remember the distance formula. We have our x1, y1, and then we have our x2, y2. Okay, and we're going to have square root of x2 minus x1 squared plus y2 minus y1 squared, and then take a square root, and we're going to have the following. So we have 3 minus -2 squared plus 4 minus 1 squared. And then we're taking a square root. So let's simplify. So negative and negative gives us positive. So we're going to have 3 plus 2 squared plus 4 minus 1, that's 3 squared. Square root. So we're going to have, so 3 plus 2, that's 5. 5 squared, that's going to be 25. Plus 3 squared, that's 9. So 25 plus 9, that's equal to square root of 34. Right, and we cannot simplify it, so we're going to leave it as a square root of 34. Okay, perfect. So we can also do multiple lines as well. Right, we can draw triangles on the coordinates. We can do squares. We can do any kind of distance formulas with those distance formula and the Cartesian coordinates in general. So let's think about one more kind of point. We might be able to find a midpoint, right? So a midpoint is going to be a point in between of the 2 points, right? So if we want to do a connection point, right? So let's take a look at the following example. So we have a point -5 and -3 and a point 9, 3, right? So we see the midpoint, right? But how can we find it? How can we find it? So we can find it by using the following. So midpoint formula. If we're given point x1, y1 and x2, y2, then the midpoint between those 2 points is going to be x1 plus x2 divided by 2, y1 plus y2 divided by 2. Okay, so let's have an example of a midpoint. And specifically, we can check that it's the case for this problem. So we're going to have, this is going to be our example. And I'm going to say, okay, well, my x1, y1 is equal to -5, -3. x2, y2 is 9, 3. So the midpoint is going to be the following. It's going to be -5 plus 9 over 2, comma, -3 plus 3 over 2. So that's equal to -5 plus 9, that's 4. 4 divided by 2, that's 2. -3 plus 3, that's 0. So our midpoint is 2, 0, and that is confirmed on the drawing. All right. So we're able to estimate things on the line, for example, right? If we have a line, we are able to estimate the midpoints and some of the points on the line. So, and actually that's going to be our following topic. Let's go ahead and introduce the line. Let's go ahead and do linear equations. Okay, so a linear equation is an equation which has x to the first power, right? X is going to be linear with constant coefficients here. So an example of a function, so f of x, right? That's what we call a function. F of x, we can also call it y, right? This is y, that's our y-axis specifically. And that's going to be equal to m, so I'm actually going to change colors here. So it's going to be m times x plus b. So this is an mx plus b form, right? And why is it a line? Well, it's a first power and it's linear. And by linear, does that mean I can have addition of x terms, and it's going to be a line when I'm plotting it on the Cartesian coordinates. So what is m? Right, m we call a slope of a line. And how do we find the slope of a line? It's essentially the line as the hypotenuse of the triangle. So in the formula, to be specific, is going to be y2 minus y1 over x2 minus x1. And in algebra, we call it rise over run. Okay. And b is y-axis intersection. Essentially the point 0, b. Right, that's when the y-axis is intersected. Okay, and what we are able to do, we are able to actually find some of the, we can find the m value and the b value, and actually we will be able to do some equations right now. So let's go ahead and say that we will have a line. We will have a line, but first, let's go ahead and draw some points. So let's say we have 2 points. First we have y-axis, we have x-axis, and we have 0, 1, 2, 3. Right? So And then we have 1, 2, 3. 1, 2, 3. So we will say that when x is equal, so we're going to have -1 and -2. So our 2 points are going to be -2 and 3, right? And then our line are going to be passing through these points. So notice we need 2 points in order to define the line. And actually, I'm going to use like this. Okay, so that's our line. Okay, so what do we know about this line? We do not know much quite yet. We just know 2 points, right? And let's write down those points. So x1, y1 is equal to, so it's going to be 0, -2. And then x2, y2 is going to be 3, 0. It's a little bit a simple problem, but that's okay. So we know how to find the slope, and the slope we will actually, I'm going to actually draw it out. So the slope in this case is this. This is y2 minus y1. This is x2 minus x1. So the slope is y2 minus y1 over x2 minus x1, which is equal to, so what is y2? Y2 is 0 minus y1, which is -2, divided by x2, which is 3, minus 0. So 0 minus gives us plus, so that's going to be 2. Over 3 minus 0, that's 3. So our slope is 2/3. How about our y-intersection? We can see that y is intersected at the point 0, -2, so we are good on that. So that means our equation, y is equal to 2/3 times x minus 2. Okay, so we can check it. When x is equal to 0, that goes away, so we have -2, which is this point. And then when x is equal to 3, 3 and 3 cancel out, so we have 2 minus 2, which is 0. So that also checks out. Now we can find any point on this line, right? By giving it an x value, we can find any point on the line. So essentially, we can also, right, this is a more, we call it analytical way of finding the equation of a line. But we can also do it is we can be given an equation and we would have to plot it, right? So if we would be given an equation, we have to plot it. The easiest way would be to follow this instruction, right? So if we want to plot it, we're going to say that the point plotting method, so point plotting, essentially has few steps here. And here are the steps. Right, so if number 1, if possible, we can rewrite the equation so that one of the variables is isolated on the side of the equation, right? And we've done that. We've done that in the sense of y is equal to mx plus b, right? We have one variable, which is y. It's also a variable, but it's a dependent variable because it depends on x, because we are playing with x values to find y. Then we would like to construct a table of values showing several solution points. So essentially, we would say we would plug in x and find y every time. Then we would want to plot these points in a rectangular coordinate system, right, on the Cartesian coordinate system, and connect the points with a smooth curve or a line. So in our case, since we're studying line, we're going to be connecting it with line. Okay, so let's take a look at this problem here. So let's say we're given an equation, right? We're given an equation, and that equation is as following. So I'm going to give an example. Will be 3x plus y is equal to 7. So we always have to solve for y unless otherwise specified. So let's go ahead and actually solve it. So we're going to subtract 3x from both sides. So we're going to have y is equal to 7 minus 3x. Okay, so that's our equation, but let's actually rewrite it in the form of y equal to mx plus b. So that would be y equal to -3x plus 7. Right, that would be the correct form of the equation. Now we can draw a table and make the table. So here would be the example of the table for this equation. Okay, so we have x values, which I've started from -2, -1, 0, 1, 2, and 3. And then we would plug in the equation, we would plug in x and simplify. Right, so we can do one example here. y is equal to, so let's do it -2, right? So it's going to be y1 here. So at -2, we're going to have -3 times -2 plus 7. So -3 times -2, that's 6, plus 7, that's 13. And that's exactly what we got right here. All right, and we can do the rest of them. Okay, so if we do all of them, right, we got the points. We got the points. And now we would plot the points as we did in the Cartesian coordinates by having the x value and the y value. So first we would put the x, then we would move up or down, and essentially we would arrive to this graph right here. Okay, so there are all of the points plotted, all right, and then we would connect them as a line. But remember, we don't have to have so many lines. All we have to have for a linear equation to be plotted is 2 points, right? We need 2 points, at least 2 points. If we have 2 points, we're happy. We are able to actually make the solution. Okay, and linear equations are the easiest equations to work with. Of course, we also can have other equations, right? For example, we don't only have to work with linear equations, but let's say if we decide to have x squared, right, as an example, let's talk about a little bit about quadratic equations, right? So quadratic equations are the equations of a form of ax squared plus bx plus c. So we have x squared, right? That means quadratic, it means second power, right? Just for a comparison. Let's say we would be given something like y equal to x squared minus 2. This is no longer linear. This is a quadratic equation because x is multiplied by itself, so it's x squared. So if we would do the table, essentially we can use the same table, right? The same table, but now we no longer have line, right? We call it parabola, right? Parabola. So it's just going to touch on to comparison for the linear equation. So this is parabola. So, and there will be the table, right? Same points from -2 to 3, but now I'm plugging them in, and of course we would be getting different numbers, but we don't really, it doesn't mean much until we actually plot the line. The line, and in this case, it's not a line, it's going to be a curve, right? And here how the curve would look like, right? So clearly it's a curve, and we have one key feature of such curve. It's that it has a symmetry, right? Along y-axis, it's symmetric. The left side is symmetric to the right side, right? And it happens to a lot of graphs, right? So graphs can have symmetry, right? This is what we call symmetry. And linear equations don't have symmetry, right? Because it's linear, and we will study later what kind of properties equations have and why some of them are not symmetric, but some of them are symmetric, right? So quadratic equations are actually, turns out to be the symmetric equations, right? So we will be learning the rules for symmetry in the upcoming lesson. Meanwhile, we will have one more topic to touch on for the linear equations. It's going to be a brief on introduction to the complex numbers. Right, complex numbers from high school algebra. You probably heard about a complex number. So, what are we going to say? This is the extra topic of today, and we're going to say, okay, complex number. So we learned about real numbers, rational numbers, integers. So a complex number, we're going to call it z. So z is a number of the form z equals to a plus I b. Okay, and the key component is that a and b are real numbers. Meanwhile, I is actually the square root of -1. Right, later on in this course, once we learned a little bit about matrices, we will see why I to be square root of -1 in mathematical sense and the graphical sense actually does make sense. Even though right now it might seem as a nonsense, but I is the imaginary number. And we will be using that fact to actually have interesting solutions to it. So if we have that case 1, if b is equal to 0, then z is equal to a plus I times 0, which is equal to a. Z is Early real number. And then case 2, if a is equal to 0, that means z is going to be equal to 0 plus I times b, which is equal to ib. And we're going to call it imaginary number. Purely imaginary number. Okay? So this is the main difference. And so the complex number system, right, it exhibits a behavior of the Cartesian coordinates. So complex number, we call it like this. It's a C, is a line. So C is going to be it's going to be a set of a plus ib, where a and b are real numbers. So it's one of the biggest sets of numbers in mathematics because it contains everything. It contains real numbers in it, but it also goes outside of the real numbers because of the complex numbers, right? And there are interesting properties of the complex numbers as we enter the addition and multiplication, right? So if we have two sets of complex numbers, right, we can have it as the following. If we have z1 to be a plus bi, z2 to be c plus di, then z1, so rule number 1, z1 plus z2 is going to be a plus c plus b plus d times I. Same thing with subtraction, right? Plus or minus, right? That will give us plus or minus, plus or minus. Okay, and then if we have multiplication, we will have a plus bi. So first thing first. Z1 times Z2 is going to be equal to a plus bi times c plus di, which is equal to, if we use the rules from the previous lesson, we're going to have AC minus BD plus AD plus BC times I. Okay, and rule number 3 is that we can have a conjugate. It's essentially similar to what we have in fractions, but a conjugate is Z1 with the hat, it's going to be A minus BI, and Z2 with the hat is going to be C minus DI. So it has an interesting property because we can multiply those two numbers and we will get a purely real number, right? And what we can do is we can do 4. So Z1 times Z1 hat is going to be equal to A plus BI times A minus BI. So we're going to have A squared minus ABI plus ABI minus B squared, I squared. And remember, I squared is -1, so we have A squared plus B squared. That is purely real number. All right, perfect. And then how do we use the conjugates? We use the conjugates if we have a division. So A plus BI over C plus DI, that's going to be equal to, how do we deal with it? We have to multiply by the conjugate. And the conjugate of the denominator. So we're going to have times C minus DI over C minus DI, which is equal to, if we simplify, we're going to have A plus BI times C minus DI over, we know that multiplying the two conjugates by the property number 4, we're going to get C squared plus D squared. Okay, and now that is a complex number. Meanwhile, this one was not a complex number because it's a fraction. We do not know which one is real, which one is complex. We have imaginary unit I in both numerator and denominator, so we do not know how it actually behaves. All right. And the last part for it is going to be that the imaginary numbers are can be expressed on the Cartesian coordinate plane. So here we would say that this is real part, real z, and here we have imaginary z. So essentially, a z1, which is a plus bi, would be expressed as a comma b. So let's say this is value a, this is value b, and that would be the point. And that would not just be the point, it would be this line. It would be always connected to the origin, right? Right. Perfect. So it was a quick overview. We will be diving more in depth next lesson, because next lesson we're going to be doing modeling with linear equations and more complex numbers, and have more deeper introduction into quadratic equations. Right? Thank you, students, and see you next time.